Audio check.
So I'll probably just.
If you think you can be picked up here, we tell people to put them on, but
Oh, okay. Then I'll put it on for the online.
Mostly for the online. Yeah.
If the person is just here, these mics should work, right?
Yeah.
Good enough.
So if you really don't like it, it's fine.
No. I didn't know what was easier. I will do whatever's easier.
Okay, sweet.
Sweet. Thank you guys.
Awesome, thanks.
Are we going to need a bell or something? So we only need these if they're the speakers. They're just here.
It's just so much safer because you just don't know what happens.
Yeah, so the Francisco.
Hello, hello. Who's on? Wait. Is it on? Hello? I don't think it's on. Good morning. Hi everyone, it's 9 a.m. sharp. Welcome to the STScI Fall Workshop 2025. And and before we start with our activities, we have an address from our director, Jennifer Lotz. Please come over.
Well, good morning, everyone. Welcome to the Space Telescope Science Institute and to this 4-day workshop devoted to one of the most exciting and dynamic evolving frontiers in astrophysics, the study of exoplanet atmospheres. Looking at the agenda for the week, we see we've got observers, we've got theorists, instrumentalists, modelers, all contributing to a shared understanding of the evolution, chemistry, and even the potential for life in worlds beyond our solar system. Space Telescope has had the privilege of being part of this story for a while. From the first atmospheric detections made with the Hubble Space Telescope to the breathtaking new spectra and phase curves emerging from the James Webb Space Telescope. And as we'll talk about over the next few days, this is just the beginning. When Hubble was launched in 1990, no one imagined it would become a pioneering exoplanet observatory. Exoplanets hadn't even been discovered yet. And yet, over the last 2 decades, Hubble's become an essential tool for probing their atmospheres. Transit spectroscopy opened the door to atmospheric characterization. Hubble's ultraviolet and optical capabilities revealed sodium, hydrogen, and even atmospheric escape from hot Jupiters. Later, its near-infrared instrument, particularly the Wide Field Camera 3, provided some of the most iconic spectra of water vapor and exoplanet atmospheres. Perhaps most importantly, Hubble has helped teach us how to do this kind of science, how to correct for instrumental systematics at parts per 10,000 precision, how to combine multi-wavelength data sets, and how to interpret spectral features that don't always match our models. Today, Hubble stands as the only observatory capable of observing hydrogen exospheres and atmospheric escape of metals in transiting exoplanets. At Space Telescope, maintaining Hubble's ultraviolet capabilities through the next decade is one of our highest priorities. So now we've entered a new era with the James Webb Space Telescope, and I think it's fair to say the exoplanet science is one of the areas where Webb has exceeded expectations most dramatically. It's become incredibly popular, with almost 14% of the JWST Cycle 4 proposals proposing to study exoplanet atmospheres. The results we've seen in just the first few years are impressive. Clear signatures of molecules bearing carbon, oxygen, sulfur, and nitrogen in atmospheres of gas giants and exo-Neptunes. The discovery of extended helium features shaped by atmospheric escape and interactions with the stellar environment. And spectra from rocky worlds that can give us the first hints on whether or not they retain an atmosphere. These are not just milestones, they are blueprints for the next decade of exoplanet atmospheric science. Webb's instruments together provide unprecedented wavelength coverage, sensitivity, and stability. That combination is letting us as a field move from detecting a molecule to answering big questions. How do planets form and evolve? How unique is the solar system? And can other planets sustain life? At Space Telescope, our role has been to make this possible. It's through proposal support, through calibration and data pipeline development, but also through community-led programs that define Hubble and Webb's legacy. The JWST early release science programs and transiting exoplanets, for example, not only delivered headline-grabbing results, but also shared reduction pipelines and methodologies that are now standard across the community. And as Hubble and Webb continue their operations, we're committed to ensuring that their exoplanet data, from raw frames to calibrated spectra, remain accessible, reproducible, and scientifically rich for everyone, everywhere. In less than a year, we're expecting the launch of the Roman Space Telescope. It won't be studying exoplanet atmospheres, but it has the potential to discover up to 100,000 new exoplanet candidates, probing samples that are more like our own solar system, and it will have a pioneering instrument to directly image planets, the STScI instrument. As remarkable as these telescopes are, the next great leap is already on the horizon: the search for Earth-like planets and their habitability. That's the vision for NASA's Habitable Worlds Observatory, the mission that's recommended as Astro 2020 Decadal Survey's top priority. It will combine the best of Hubble, Webb, and Roman legacies, operating in the ultraviolet to near-infrared wavelengths, equipped with advanced starlight suppression technology and the most sensitive UV spectrograph to date. For the first time, we'll be able to directly detect reflected and transmitted light from potentially habitable planets and search for atmospheric signatures, hydrogen, oxygen, ozone, methane, water vapor, that could hint at Earth-like conditions. We here are deeply involved in the early studies of this mission, developing operations concepts, data analysis frameworks, and the science cases that will guide its design. And we look for you, the community, for leadership, for creativity, and critical thinking as we together help define what questions we want that observatory to answer. So as you start this next 4 days of discussion, collaboration, analysis, and probably a lot of debate, I'll leave you with this thought. Every spectrum you extract, every model you refine, every signal that you tease out from the noise, all of it is contributing to a larger story. It's the story of how we as a species are learning how to understand the physics that shape other worlds, and through that, we are learning something profound about our own world. So thank you all for being here, for doing the work that you're doing, and for pushing the boundaries of what's possible. I hope you really enjoy the next 4 days.
Thanks, Jen. So I want to show you just a little bit of history of the STScI workshops. So I tasked Julia Darrows from the institution archive to look up what was the oldest workshops that we had here at STScI, and they date back to the 1980s. I think the earliest one was 1985, but we couldn't really find anything written down in paper about it. The earliest one we found something written down was in 1986 for a workshop from the SDOS users. So SDOS used to be the data analysis software for the Hubble Space Telescope. And it stands today as there's a happy hour that we're going to have on Wednesday whose name derives from the SDOS software, and it dates back to these times. Now, the first workshop about exoplanets, I think, according to my research online, was Planets Beyond the Solar System, the Next Generation of Space Missions in 1996. So this was only 1 year after the discovery of 51 PAC-B. And it discussed many things, many aspects of exoplanets, like radial velocities, astrometry, direct imaging. And it also mentioned the Next Generation Space Telescope, which would become James Webb later. Now, the first STScI science workshop about the next Hubble Space Telescope was held in 2003, and it really seems very similar to what we now know as the Habitable Worlds Observatory. But it's also interesting that they were not really happy with the 4 to 10 meter class, and just the year later they had a workshop about a 10 to 30 meter UV optical space telescope, also here at STScI. And the most recent planet-related STScI workshops were enabling the transiting exoplanet observations with JWST and planning solar system observations with JWST, both in 2017. So it's been a while since we last had a workshop about planets. So it's about time we have this one. So for this workshop, we are tackling several science questions, which you're probably already kind of tired of seeing them, but the idea is to workshop answers for these science questions. These are some of the most burning science questions that we have right now that are related to atmospheric escape and replenishment in planetary systems. Our agenda very roughly looks like this. I want to highlight that in the evenings we have events happening on Tuesday. We have a reception this evening. Tomorrow evening we have the SDOS happy hour. Apparently it's the longest running regular meeting of STScI dating back to 1981. It has an interesting history behind it because in the beginning it was supposed to be the SDOS work meeting, but they would run out of things to talk about, so they would just have beer. And the tradition stands to this date. On Thursday, your evening is free and you can do whatever you want. And on Friday evening, you can go home. But before you do that, I invite you all to join the white paper planning and discussion in the afternoon, right after our final session on Friday morning. Now, a bit of logistics, local information, you can find that all in the welcome packet, which is available online. You can check it out either on the website or on that QR code. has some important information about places to go, things to do, public transportation, and all of that. I've written down my local favorites here for coffee, Mexican food, and pizza. So if you want to give those a try, that's my personal recommendation. We also have a workshop bingo. So I realized now that bingo is probably a bit outdated for workshop icebreakers. When I went to ExoClimbs earlier this year, they have the meme competition, and there were prizes and all of that. So that was a bit more exciting than bingo, but I think bingo can be fun too. So yeah, and this is all in good fun, so don't take it too seriously. But if you do shout bingo during someone's talk, you may get a prize from me. Please don't do that. Anyway, a big thank you to these folks, James Owen, Dave Brain, Christina Kizliakova, Kaylee Rockcliffe, Manas Alam, Patrick McCreary, Lakeisha Ramos Rosado, Victoria Ramnarine, Shemaya Smith, Kevin Flynn, Gary Gilbert. These are all people that helped the workshop happen. So I would invite you all to applaud them. So all of them are here except James and Christina. They could not come, but if you want to chat with any of us, please come. Now, I invite you all to network quite a bit in this workshop. And with that, we can finally start with our activities. Thank you.
All right, so for our first session on the impact of chemical makeup in atmospheric retention, I'll be your chair. We're going to start off with an invited talk. We're honored to have Ruth Murray-Cla to tell us, to kick us off and tell us all about it. I'll bring the talk up. I think you can turn it on. I'll give you 35 on the clock. Thank you.
Great. All right. Hi, everybody. I'm really looking forward to the workshop. So I was asked to get us started with workshopping processes by which atmospheric chemical makeup regulates hydrodynamic escape. So normally when speaking, I would start with observations, but in this context, I'm not going to. It's bright and early. We're going to talk about some terminology, then we're going to do some physics, and we'll get observations a little bit later. All right. So just to get us started, I'm going to give a little terminology, at least the way I use it, and if others in the room are using this terminology differently, I invite you to let us know. So there are two classes of escape mechanisms, each of which can be thermal or non-thermal. There can be kinetic, so you lose individual atoms to space, or hydrodynamic. So the bulk of your outflow, you have a bulk outflow in a collisional fluid. And these processes can either be thermal, the kinetic version of that is Jean's escape. The hydrodynamic version of that is, is hydrodynamic escape. That's what I mean by hydrodynamic escape. Or they can be non-thermal, and let's just mention these. I'm not going to be talking about them. Non-thermal processes, often mediated by magnetic fields, are very important for solar system planets. And planets with relatively low mass loss rates. I'm sure we'll hear more about that later. On the hydrodynamic side, we can have Roche lobe overflow. You can be pulling mass off just from tides. This usually requires extreme tidal conditions, but tidal corrections to a planet's potential well are often important, even in not extreme cases. You could have ram pressure stripping. If you have extreme stellar winds hitting a planet, so extreme that you could push and confine the winds interior to their sonic point radii, and I'll tell you what that is in a second. I'm sure most of you know, but in a moment we'll get to that. Then you could strip your planet. That again is an extreme situation. Or you could have collisional erosion. This isn't important for Jupiters, but it could be very important for super Earths and lower mass planets. So again, I'm going to be talking about thermal escape in this talk, and in particular, I'm going to be talking about hydrodynamic escape, and thinking about how the compositions of planets can affect this process. And the first sub-question of that is, well, is your outflow hydrodynamic? So let's just remind ourselves of what a hydrodynamic outflow is. Let's start with an isothermal Parker wind. It's fluid, that means it's collisional. Let's make our atmosphere be hydrostatic. It's unhappy because pressure at infinity is greater than 0. Sad, it won't stay hydrostatic. Boo, it accelerates the gas outward, and you end up with an outflow. Okay, this outflow gets the energy for pushing gas off of the planet from the assumption of it being isothermal. And in fact, if you take this to infinity, you need infinite energy to do this. So that's not going to be real, but it's actually a reasonable approximation in a lot of cases, as long as you're not going out to infinity. All right. These Parker winds, and these, of course, were developed originally for the solar wind, which is not, in fact, collisional. You have to rely on, magnetic flux tubes bouncing around or something and then waving your hands, and it works pretty well. But for planetary atmospheres, it's actually a classic Parker wind. It is truly collisional. It's driven by pressure in the gas. They have a critical point at the sonic point, where the outflow velocity is equal to the sound speed, and it's about equal to the escape velocity. And if you want to get that critical point formally, it's similar to the calculation of a de Laval nozzle, which gave us rocket engines. You put together your mass and momentum equation, and you find that in order to go from sub to supersonic, you have to pass through the sound speed at the critical point. But just to wave my hands around a bit and give a little bit of intuition why this might be this way for winds from planetary atmospheres, let's think about what if you started with your outflow velocity equal to the sound speed less than the escape velocity, closer into the planet. Well, you actually can't get a steady solution in this case because you need to accelerate more to escape your potential well. You're not above the escape velocity, but you can't shout upstream in a supersonic flow, so the flow can't communicate with itself all the way up to where it would reach the escape velocity, and you can't get a steady solution. So formally, you end up with a double-valued solution if you give it an initial condition that starts like this, and it's non-physical. But it's basically because it's not causally connected. On the other hand, if you want to make your velocity equal to the sound speed and escape, beyond where the sonic point is, you have to ask yourself, how did it actually get accelerated? So we're going to do equations. Woo! F equals ma. We got some forces per volume equals mass per volume times acceleration, dv dt. But this is a steady flow. So the only way you get a dv dt is by getting dv dr times dr dt. But dr dt is just v. So that's rho v dv dr. So we get our nice steady state. I'm just going to get rid of these so it looks nicer. Momentum equation. And if we look at that order of magnitude, we've got a gravity term, a pressure term, and a velocity term. And you can see directly that that velocity term, when the velocity is smaller than the sound speed, that term is smaller than our pressure term. And so you just get hydrostatic equilibrium. And the scale length, when your velocity is less than the sound speed, is the sound speed squared over the escape velocity squared times the distance, which is just your standard scale height. Nothing special has happened. But why did I do this? So once your sound speed is greater than your escape velocity, then that length scale is greater than r, and the velocity really stops changing much over distance r. So this, I haven't proven anything, but I'm trying to give some intuition. You're having a hard time accelerating yourself. If you didn't get to the sound speed by the time you got to the sonic point, you're not going to get there in this isothermal wind. And in fact, when you see these wind outflow solutions, even when in the full glory, you find that once they've gone past the sonic point, the velocity starts, leveling out often, and you don't accelerate dramatically beyond that point for the same reason. Okay, so we've got our Parker wind. You get accelerated through the sonic point unless you're confined by external pressure, in which case you can just never go supersonic. And now we can look at this and say, okay, what happens when your temperature goes down? Well, your sonic point radius goes up. And that means that your mass loss rate goes down. Your radius is increasing, where your velocity is equal to the sound speed. But we just said that when your velocity is small compared to the speed of sound, you have a roughly hydrostatic atmosphere. That means that your density is falling off exponentially. And that falls off faster than the radius goes up. And you end up with a lower and lower mass loss rate. And you're also more and more diffuse at the sonic point. OK. So this whole story, so that's the basic isothermal Parker wind that most, if not all of you, I'm sure have seen before. But I think it's useful to have gone through this to give us some context for now thinking about what's going to be happening in a more detailed atmosphere. OK, so acceleration by pressure requires collisionality. You can't shout upstream in a supersonic flow, so what happens beyond the sonic point doesn't matter. But what we've shown is that if you give us an atmospheric density, add in a radius, and you tell us what the escape velocity is at that radius, then we can use hydrostatic equilibrium to estimate whether the flow will be collisional at the sonic point for the sound speed that goes with that temperature and mean molecular weight of our atmosphere. And you can just plug this in. This is the density, and you can see it just depends on that escape velocity and the sound speed. And this ratio here is often called the escape parameter. That sound speed squared, again, depends on the temperature and on the mean molecular weight. So immediately we can say, well, if you have a higher escape velocity where you're launching your wind and or a higher mean molecular weight, then you're actually less likely to experience hydrodynamic escape in the first place because you're more likely to be collisionless by the time you've reached your sonic point. So that should be intuitive, right? If you have a heavier atmosphere, it's harder to launch a wind, and it's going to be harder to keep it dense enough, high enough to stay collisional, to stay fluid, and you're more likely to transition from hydrodynamic to kinetic escape. OK, so now where does the energy come from? It can come from anywhere you like, and I don't mean that snidely. I mean that really, anywhere. Like it's just actually heating. Like there's nothing special that's happening here. So the two main sources that we think about usually are bolometric heating and photoionization heating. But if in your particular context you have another way to heat the gas, rock on. So bolometric heating. Bolometric heating, by which I mean just the bulk luminosity from the host star can heat your atmosphere. This tends to generate an isothermal-ish radiative layer, and I'm sure we'll hear lots of ways this week in which it's not actually isothermal, but I'm going to say it's isothermal-ish, and that's because bolometric irradiation from the star contains a lot of energy. It's mostly re-radiated away. As the planet's thermal emission, you're usually not at a loss for incoming energy. And so we've already talked through what happens in an isothermal wind. We can write down immediately what's going to happen. So the requirement that your escape velocity of your sound speed not be too large for a hydrodynamic outflow limits this to puffy planets. And why do I say puffy? Because usually the bolometric heating is what sets the actual optical visual size of your planet. So you're not just puffy in the sense of where you're launching your wind. You usually, you're talking about a planet that looks puffy. Higher mean molecular weight means you need larger temperatures to do this. So it's easier to be puffy if you're a hydrogen atmosphere, harder if you're not. And when this is active, it can dominate because your launch density can be really large. You can launch really dense wind this way if you are in the right situation. So what really matters here is what's the radius of your planet and what's the density. That's what we said on the previous slide. What's the density at a particular radius? And core-powered mass loss, for example, appeals to long-lived puffiness. So if you have a puffy atmosphere, then maybe you can lose a lot of mass with from just getting at least your launch energy from bolometric heating. Okay, the other standard thing that we think about is photoionization heating. And photoionization heating, in contrast, relies on high energy photons, usually EUV, sometimes X-ray, coming from the host star and hitting the upper layers of the atmosphere. And the key thing here is that you have your ionizing photon that comes in. It ionizes. I've got a hydrogen here, but it doesn't have to be hydrogen. It can be really anything. And the cross sections for most things are not that different. You kick off an electron. It has some extra thermal energy. It collides with its neighbors. It distributes that energy around, and you get heating. And this mostly happens at about 1 to 10 nanobars in the atmosphere, which is pretty diffuse. And up there, cooling can be inefficient. And so you get to keep all of that energy that you got, maybe, and put it into escape. So exactly where you're launching, where you're putting in your energy depends on what photon energies you're using. If you're using X-rays, then you're generally, instead of hydrogen, you're depositing this in metals, because metals, you can bump out a K-shell electron with a pretty high cross-section using a high-energy X-ray. But both metals and hydrogen will be ionized by UV, broadly speaking. And the key thing, again, is that the cross-section for this process is super large, so this happens at very high heights in the atmosphere. All right, so again, you're depositing your energy basically at optical depth 1 to whatever is doing your photoionization. That tends to be nanobar-ish pressures. But for high X UV flux, you can eat in a lot deeper. You end up with ionization equilibrium, and you can go into substantially higher pressures this way. And the base density here is no longer a free parameter. It's set by the heating process. And also, we can just note that some atmospheric components may not be mixed up to this level because it's at such low pressures. Okay. So let's just think about this photoionization heating from the perspective of two classic-ish thermospheres. We have the Earth and Venus. I guess I can say that's classic. Earth is classic. EUV is absorbed in our thermosphere. It heats it up to about 1,000 Kelvin. And what happens to most of that energy is that it's conducted down until it reaches a high enough density where carbon dioxide can radiate it away in 15 micron emission. Meanwhile, in hot Jupiters around old stars, that same EUV is absorbed by hydrogen in the upper atmosphere, similar pressures, and that drives a collisional fluid outflow. And the main difference here is that more energy is being deposited in this case. So it heats the atmosphere up hotter and drives it out before it has the opportunity to conduct that energy down. Like the conduction is still operating, but it just cannot actually conduct this energy down at anywhere near the rate needed to balance the high heating. Okay. All right, so this is just to, again, to say for the Earth's atmosphere, right, you have your exobase where it becomes collisionless. Genes escape is happening there. It's minimal. We don't have a hydrodynamic outflow. Instead, conduction of the heat, the deposited heat is conducted lower and then is radiated away. All right, so how can we think about more generally whether you're going to end up with this wind situation or genes escape, kinetic thermal escape from a wind? Well, we can actually write the mass loss rate in a normalized way that you get. If we take our atmosphere to have roughly the same temperature throughout, which again is not going to be good, but it's an okay approximation for thinking this through. And what I've done here is put this escape velocity over sound speed and thermal velocity are the same thing. So that same parameter we were looking at before, and a normalized mass loss rate. And if this ratio is about 1, you just immediately lose your gas. It's not bound at all. Then it goes into a hydrodynamic wind. And then at some point, when it stops being collisional at the sonic point, it moves into Jean's escape. And because the heating is happening from the outside, and our base density is not a free parameter, we can actually write the relationship between the base density and the density at the sonic point, which tells us whether we're collisional, just in terms of the ratio between the collisional cross-section and that XUV absorption cross-section. So you can actually pretty nicely get this transition in this dimensionless space between a wind and Jean's escape. Okay, so what can we do with this? Well, we need one more piece, and it was on the bingo card, getting our first bingo, I think. We all know that if you take the energy required to lift atmospheric gas out of a potential well, you can turn that into an energy limited escape formula. Take all the energy that you put in in this case, radius RP, use it to lift gas out of the potential well. And I'm going to relax this in a second, but let's start with this. And you can get the maximum mass loss you can drive from your input energy. That radius, remember that's the radius that was our boundary condition. It comes into this equation to the third power. So the altitude where this is happening matters a lot. And that's set by the lower atmosphere and in the interior of the planet. So I'm just talking about the wind, but the interior structure of the planet for all these processes matters a ton because it sets the radius where all of this is happening and your escape velocity. Okay, so I'm going to take that dimensionless plot that I had and I'm going to dimensionalize it for a hot Jupiter made of hydrogen. And I'm going to put a vertical line at the energy limited escape m dot. Okay, and then I'm going to see where it hits the curve. And for a hot Jupiter, it hits the curve at a wind at 10 to the 4 Kelvin. And if you make a wind at 10 to the 4 Kelvin, it's just fine for an old star like an HG 209 458b. No substantial local energy loss, and that's indeed what models for those sorts of planets give you. Hydrodynamic outflows with about that temperature. What if we did that for Earth, for hydrogen, put on that energy limited escape rate? You'd get an 1,000 Kelvin Jean's escape kind of situation. What if you made Earth carbon dioxide? Oh, and actually, sorry, before I move on from this, you get an 1,000 Kelvin Jean's escape situation, but if you made this model, if you wrote it down, this isothermal Jean's escape model, you'd say, oh wait, conduction is actually really important for that model. So this isn't sufficient. You need to care about the conduction, and that's indeed what happens in Earth's atmosphere, though it's not a hydrogen upper atmosphere. Okay, what if you did the same thing for carbon dioxide for Earth? Well, you'd get Jean's escape at like 10 to the 4 Kelvin, and that's just nonsense. You know that you'd either dissociate or molecularly cool. And so just looking at this without those additional energy terms is just insufficient. Okay, so that leads me to the second piece, which is how much of the input energy goes into escape, right? So for an HG 209 458b old hot Jupiter, energy limited is not so bad. But
but that's not true in all contexts. And so I think that this is really where having a different composition, if you know that you're hydrodynamic, right? So your composition makes a big difference to whether you're hydrodynamic or not. But if you know you're hydrodynamic, that was part one. If you know you're hydrodynamic, then it's also going to make a substantial difference to how much of the input energy goes into escape. So we have 3 potential fates for deposited energy. The second one we already talked about. It could be conducted lower in the atmosphere than radiated away. Again, higher mean molecular weight atmospheres have an easier time doing this just because it's harder to launch the wind. Remember, it's hard, you get conduction when you're not launching things so quickly that you don't have time to conduct. It can also drive an outflow, which might be energy limited, but there are several potential structures. And I'm just going to briefly mention one interesting aspect that we'll hear about that from Yaotong later in the week. If we look at, this is radius scaled to a microbar radius atmosphere from Yao's CMIST model, which includes both the interior structure and an outflow model using WINDY, which Maddie will tell you about in a moment. And we can look at the temperature structure for a hot Jupiter and for a superpuff, as Yao will talk about later in the week. At these really low gravities for superpuffs, a large fraction of the energy actually goes into heating, not into escape. Never mind radiative cooling or any of these things. Just when you put in energy, a lot of it just goes into making the gas hot. And so you don't end up with energy limited escape according to the classic energy limited escape formula. Okay, yeah, we'll tell us about that later in the week. Okay, so then I'm gonna talk about this last one. What about radiating away this energy? And this, again, really depends on the composition of our atmosphere. So radiative cooling can reduce escape substantially for Jupiters, particularly at very high surface gravities or lower XUV fluxes. And for small, low surface gravity planets, possibly all the time. So let's talk about the high gravities first. So at high gravities, escape declines. You can see this in both of these papers. And I'll just highlight HD 189.733b here, which is another one of our classic hot Jupiters, which is, just over the edge of the declining escape rate seen in these plots. This is a scaled escape rate. So our efficiency of atmospheric escape is declining at high surface gravities. And just to give a qualitative sense of that, here's an outflow from a nice, not extremely high gravity Jupiter. We've got three panels because there are 3 different stellar wind strengths. But my point here is not that. It's just driving a nice outflow. But for HD 189, a similar simulation looks more like this. It's just kind of getting itself out of the Roche lobe. It's going through the Lagrange points. You can see it eking its way over. Okay. So you can see that lack of outflow efficiency in this plot from Madelyn Broome, and she'll tell you about the code that she made to make this in a moment. But you see this blue region here where planet masses are high and radii are not super high. Along the edge of the plot, you have low loss efficiencies, high gravity planets. And I'm not going to make you go through more equations, but basically to drive a wind, you have to put in enough energy over an outflow time scale to get the wind to launch. The maximum temperature you can possibly need is the escape velocity, since then the gas is immediately unbound at the base. And so if we look at a couple of different example planets, we can see what this means in practice. This is a sub-Neptune, where the details aren't super important, but here's an outflow with 1 input flux, and then an outflow with a flux 10 times higher. It gets a lot hotter, right? Because you're you're putting in more flux, you get hotter. But if you do this for a high gravity planet, the same thing doesn't happen, because just making you a lot hotter would put you above 10 to the 4 Kelvin, where radiative cooling from atoms in Lyman alpha from hydrogen and also metal ions kicks in. And so you can make this thing, the orange curve, 1,000 times higher than the blue curve. And this is for HG 189.733. That's the one I was showing you. And it gets a little bit hotter, but not nearly as dramatically hotter. And what's happening to all of that extra energy? Well, it's going into radiation. It's getting dumped by radiative cooling. Okay, so just an aside before I do the summary about these high gravity planets. Even giant planets have substantial metallicity. This is some recent work from Yayati Chachan showing that even super Jupiters appear to have several times solar metallicity. So metals can enhance the radiative cooling compared to hydrogen Lyman alpha. And that can actually substantially increase the amount of energy you dump, but they may not be lofted high enough to join the outflow. And I expect Mateus will tell us about this and maybe some other people later in the week. So if you have the metals, they're going to matter. And I'll just give a brief plug for Ethan Schreier's poster. We've been thinking about in extreme cases where stellar winds are not able to blow out a torus around a host star, can we look for this? And this is a place where, in principle, we could actually look for metals that have been escaping from planets and separately from transits. So I don't have time to go into it, but I encourage you to go check out Ethan's poster. Okay, so this is where I was. So the summary here is that high gravity planets dump energy into Lyman alpha and metal lines if present, because multiple ionizations are needed to put in enough energy to get the gas out of the potential well. The ionization is fractioned high. Temperatures try to reach escape velocity near the surface, but cooling processes thermostat this to lower temperatures. So the more metals you have in these outflows in these high gravity situations, the more effective this cooling is going to be. Okay, but even more extreme, oh wait, sorry, I have to say one more thing before I get to the marksheet. Okay, that's for high gravity planets, but even regular warm Jupiters dump fractionally more energy into radiation if you put them at lower fluxes. If you take a hot Jupiter, and this is from Renata Frelick, who will be speaking a little later, and you take your hot Jupiter and you move it out to 0.2 AU, then look at this blue curve. Instead of most of the energy going into driving an outflow, only a smaller fraction of it is, and most of it's actually going to that purple curve, which is Lyman alpha cooling. And you cannot reproduce this just by putting in a fixed efficiency factor. And it's because these things are high gravity compared to the flux that they're getting. So if we, even though a hot Jupiter right next to a star is kind of energy limited-ish, that doesn't extend when you move it. Okay. Yes, you can't capture this behavior using fixed efficiency. Okay. Even more likely to be cooled by metals and to depend on your composition is lower mass planets. So lower surface gravity planets, and I haven't gotten to that yet, but I'm showing this is a plot, again, from Renata, looking at one of those Jupiters from the previous plot, and she's been able to separate out the layers of these atmospheres, and you'll see why I'm showing you this in a second, into molecular hydrogen layer, atomic, and ionized hydrogen. And this layer is cool. This has been known for a long time, like from Rodriguez and Garcia Munoz, H3 plus cooling, molecular cooling, Lyman alpha line cooling, and then up at the very top, PDV work. And then if you look at, there are many lines on this plot, but what I want you to look at is just the red one. For your hot Jupiter, that molecular cooling only extends in that very lower layer of the atmosphere. But if you make the same kind of model for a sub-Neptune with a lower surface gravity, check it out, the red line goes all the way out. And you can get molecular line cooling throughout the outflow. And this extends to other molecules. And we know that molecules are excellent coolants. And Renata's going to be telling us later about some of the work she's been doing extending this to other compositions. So, you know, when you are, and we also know that these smaller planets, they're not hydrogen. They're full of heavier stuff that can make molecules. Okay. So so that's where I'm going to end because I think I'm out of time. What processes? So I'm going to take my last 2 minutes to go through my summary. What processes can tell us about how the chemical makeup regulates hydrodynamic escape? That was the remit here. So first we talked about higher mean molecular weight. This is very intuitive. Higher mean molecular weight enhances the likelihood that you'll have kinetic escape rather than hydrodynamic escape. So a much lower escape rate, right? It also makes it more likely that you'll have radiative cooling from high gravity atomic line cooling and high gravity planets. And the more metals that you have, the more effective that cooling is going to be. But in lower gravity planets, it's even more extreme. These likely experience more radiative cooling because molecules survive. And if you're in these really super puffy planets, then you end up in this temp regime Yao is going to tell us about, where a lot of the energy goes into heating. But even when you're not in an extreme planet, molecules are going to survive in these outflows, and they're going to cool a lot. So what these two upper bullets say to me is that we've been kind of lucky that hot Jupiters are in the energy-limited escape regime. And if we push out of that regime in almost any direction, it's not really going to be energy-limited anymore. And it's going to depend on our composition. Okay. All right. We also said that the launch radius for these winds makes a big difference. So the composition of the deep atmosphere, which I didn't talk about, but I'm sure others will, and the interior of our planet is going to make a huge difference to our loss rates. And this, of course, also depends on composition. And finally, the composition of our outflow, doesn't just depend on the atmosphere's composition, but also on how much is mixed up into the wind. And this also affects how much atmospheric loss can affect fractionation of planet atmospheres, which I did not talk about, but I assume will be talked about over this week. So I'm going to end there, and I'm looking forward to the meeting. Thanks.
Questions?
Yeah.
Hi, Mike Chapman, University of Colorado. I'm wondering, to what extent do you agree with the statement hydrodynamic escape is the last resort of a desperate atmosphere? And what caveats you would put on it?
Yeah, sounds good to me. If you can radiatively cool, you'll do it. If you can conduct your energy lower, you'll do it. Of course, conduction is a two-way street because it puffs you up and makes it easier to blow material up, but it also can send you down where you can radiate your energy away. So it can do either of those things. But yeah, you drive an outflow if you have no other place to put your energy. So yeah.
Any other questions?
I was taking notes during the talk, so there was one particular thing that caught my attention when you mentioned the base density is not a. Elaborate on that.
Sure. If you're photoionization heated, then your base density is not a free parameter because your base density is set by where optical depth is about 1 to photoionization for whatever your dominant, heating photons are. So if your base is neutral, you can just say it's, the density there times the scale height of your atmosphere times the cross-section for photoionization is 1. That gives you your density. If you have more flux, then you have to do ionization equilibrium because you can go to higher densities. But in either case, you can just calculate what that density is based on your input flux. So you don't get a choice. What you can choose is what the radius is where that happens. And that's set by the lower atmosphere and interior model. But the actual density is not a free parameter when you're photoionization heated. Yeah.
Awesome. I invite anybody online to submit questions. There's a chat feature, but there's also a Q&A feature available. So go ahead and submit questions there. In the room, Park.
Park Boy, you're excited. And I'm curious, Ruth, I think we hear about energy limited state. I think sometimes people mean just using the energy limited equation, and you mean something different, potentially. I'm curious if you could comment on that and when it is useful to use the equation, say, like modifying the efficiency factor.
Yeah, so, what I mean by actual energy limited escape, right, is that all of the energy minus what actually just went into the ionization. So you always lose like half of it to that. But, order of magnitude goes into lifting gas out of the potential well, right? And that is, as long as you pick the right radius, that is indeed a limit. Incidentally, if you pick the observed radius of the planet, it is not a limit because you can put in your energy substantially higher than that and you can get a mass loss rate that's larger than what you would estimate. So, so it's not always actually an upper limit if you don't pick the right radius. But in any case, it is, you are not actually allowed to get energy from nowhere. So, if you pick the right radius, it's a limit. But you're right that you can always just stick an efficiency factor in front of it. And for any individual planet, if you can make that number anything you want, then by construction, you can always get the right mass loss rate. But I would say that that's only really useful if when you change relevant things, that efficiency parameter is roughly constant. If it depends on all sorts of things, which it will, when you're in these non-energy limited regimes, then you can still use it as sort of a guideline for is this a lot or a little bit of escape, but you're not going to be able to use it to get a sense of the physics of how things scale. So as a theorist, I find it unuseful. But that doesn't mean that you can't. That doesn't mean you can't write it down and say like, for this particular planet, it's 10% efficient. Sure.
Any other questions? Mike again, yeah.
So, Mike Jeff from University of Colorado. How do we begin to tackle this, what seems like an impossibly large problem of different compositions of atmospheres, different molecules with different band systems, different interactions by collisions? What's the outline for us as a community to begin to break this problem down into tractable parts?
I don't think it's an impossible problem. I mean, for me, coming from the exoplanet community and coming from, hot Jupiters that are roughly energy limited, a useful direction seems to be to ask, at what flux are you going to be hot enough that you're going to be thermally dissociating or photo dissociating all of your molecules in your upper atmosphere, so that the outflow is essentially atomic, at which point the outflow is not, there are many fewer free parameters, right, at that point. And then can we understand, how far you have to be from your star where those molecules start surviving? and preventing you from being in that limit. And that should be a meaningful observational distance, I think. So that's not the only approach, but I think that's one way of thinking about it. I mean, you can always photodissociate a layer on the top of your atmosphere. And if that layer is big enough to occupy what Leo was asking about, the density where you're driving your wind, then your outflow may not actually care about the molecules below. But if you can keep some of those molecules like in the outflows that Renato was showing, then they will be important coolants. So I don't think it's an impossible phase space to go after, but I think we have to do it one step at a time, as always.
Yeah, it seems impossible, but there's always a way to tackle it.
Job security. Any other questions? We got time for a quick one.
Yeah, I don't want to thank Mike, and I've been hopping, but okay. Well, that just raises this observation question that I have in mind for a little bit, which maybe is a slide. Sorry, I don't see it.
No. That wasn't a sigh at all. I was just the lens in my face. I can't get away from
Yeah, which is in that phase space. Like, can we define a boundary between hydrodynamic with models hydrodynamic escape versus kinetic escape that would be clear enough that we can actually go out and try to observationally test if we have, like, say, strong enough observational upper limits that we can get for non detection to see, like, oh, it did turn on here and it was turned off here, and our models are right.
I think we will be able to, if anyone in the room has done it, we should say so. But it hasn't happened yet. But sort of the way that I was talking through this today is a direction that I think is going to be useful for doing that. Yes.
Awesome. Let's thank Ruth again. Great. All right. Next up, we have Madelyn Broome with a talk on the mass loss, metallicity, and mystery of HD 1A9733b.
Hi everyone, I'm Madelyn. I'm a final year PhD working with Ruth and a couple other folks here. It's amazing to see those of you I've seen again. If you've not been to an atmospheric escape conference before, welcome. I'm very excited to meet all of you. Please come talk to me about everything. So my goal for this talk is to offer you some tantalizing Costco samples of what high metallicity forward models can tell us about atmospheric escape in hopes that you brilliant folks will take those home and make the whole hot dog, or hire me to make the hot dog. Okay, so I'm going to briefly go over WINDY, the model that Ruth mentioned. We'll also talk about how metals are going to influence the observables, some of the outflow energetics, and ultimately mass loss rate trends. So Ruth gave us some of this background already, but to highlight some of the reasons we care about X-rays when we're talking about metals and metallicity is not only because young hot stars are going to be strong in the XUV, metals also have extremely large X-ray ionization cross-sections. So you can see on the right, as a function of photon energy, in the X-ray energies, oxygen, even weighted by like abundances, this is 1 times solar, hugely dominates over hydrogen in terms of its ionization cross-section. So it's going to absorb a lot of X-rays at high energies. X-rays also have the ability to ionize more than 1 atom per photon. You get multiple secondary ionizations when you account for X-rays. Metals have that higher mean molecular weight Ruth mentioned, and as we saw in that previous plot, there's an updated version in Ruth's talk. Planets are likely supersolar in metallicity. And last but not least, for the observers in the room, metals and outflows might be observable, and they may not suffer from the limitations of Lyman alpha and metastable helium. So what is WINDY? In brief, an open source 1D multi-frequency, multi-species, hydrodynamic, transonic, Parker wind, steady state photonization, relaxation forward model in C based on Ruth Murray-Cla et al. 2009. You don't have to remember that. I will tell you what details of that are important when we get into the physics of this model. So limitations, this is a steady state model. We do not model diffusion or drag. If you want that, go talk to Matthias Schulich. We don't deal with magnetic fields, which may be important for some of the results I'm going to mention in a minute. And our assumptions, because this is a 1D model, are only valid up to the Coriolis turning radius, where that wind starts to turn and go into a tail. So windy has the ability to take in our planet parameters. We can adjust metals that are in the outflow and the metallicity. You can adjust stellar spectrum and boundary conditions, or if you're lazy, just set these to the defaults. Outputs, we get out a temperature, density, velocity, ionization fraction, and column density, which is a proxy for optical depth, as a function of radius. And so we can use those to calculate mass loss rates. So in pictures, we smooth a stellar spectrum. It's incident on a planet. It's absorbed each of these different energy photons at different heights in the atmosphere. And then we assume that this wind is launching at some radius RxUV and flowing out, being subsonic from some point below the wind to that sonic point that's a large X at the top. And our relaxation model just solves for this reason, and we use an integrator to solve outward beyond that. But for calculating the mass loss rate, we are only concerned with that region up to the sonic point. For folks that care about the energy conservation or the energy in this model, we do a balance of effective heating, ionization heating, line emission, only oxygen and carbon and hydrogen at this point, though at high metallicities it's been shown that iron and calcium will also be important. And I keep going to more and more posters and talks that have different lines that are also proving to be important. So pay attention to line cooling when you're modeling these outflows. PDD work, recombination cooling, and the model that is not online, but that I have been using for the plots in this talk, also have conduction cooling. And then below the wind, as Ruth mentioned, we assume this is dominated by a balance of volumetric heating and cooling. So when we add metals to these outflow models, how does that influence our observables? So when we talk about Lyman alpha and metastable helium, two of our classic signatures, what we're really thinking about with these probes are velocity and ionization fraction, as well as the temperature structure. That's what we need to calculate these. So let's take a look at what adding metals does to the quintessential example, HD 209458b. So you see immediately that there's a small difference in the density structure, but a noticeable difference in that velocity structure, which will have an implication for our Lyman alpha signature. Then our ionization fraction becomes quite different when we add metals. We see that hydrogen is ionized more quickly. And the temperature structure, not a huge difference, but a difference of 1,000 Kelvin at long distances from the planet. And nevertheless, we only see a factor 3 reduction in the mass loss rate on this planet. So mass loss rate isn't necessarily the greatest indicator of what our observables are going to be. So before I even knew that folks were going to talk about M dwarfs in this talk, or in these sessions, I became intrigued by the differences that you get when you have an M dwarf versus, say, a G star spectrum in blue. And so these are scaled solar spectra to the same total flux. I haven't adjusted any of the realistic parameters like the stellar mass, but we can see immediately that the effect on your outflow profile for just having these two different spectra is going to be pretty dramatic. We see a difference of 350 Kelvin. This is just for a pure hydrogen helium outflow. And a difference in our relative ionization fractions of hydrogen and helium because of where the energy is distributed in these SEDs. And so when we add metals, even with metals, we still get this 300 Kelvin difference in temperature structures. And on the right, I've changed the color scheme a little bit just to indicate, make it easier for your eye to follow the differences in the M dwarf, which is now dashed, and the G, which is solid lines. And so we see that having these different input SEDs is going to change the distribution of where our energy is going on our atmosphere and which species it is ionizing, which will ultimately affect our absorption. So the aforementioned 189733b is a planet with mysteriously deep X-ray transit. For some reason, we are getting this 6 to 8% absorption compared to the optical, which is about a 2% transit depth. And there are some folks here who have specialized in observing that, so talk to George King some more about that. And so the original Papenhager paper posits that this could be due to atmospheric escape. And the calculation they do use in the energy limited mass loss rate is that you have to get a mass loss rate of 10 to the 11 grams per second in order to get a large enough cross section, seen here in black, to absorb sufficient X-rays to get that 6 to 8% transit depth. But when we use our forward model, we find not only a factor of about two orders of magnitude lower mass loss rate, we see that the absorption cross-section of the planet is actually quite small. It's mostly the lower altitudes in the atmosphere, upper atmosphere, that are doing this absorbing of X-rays. So that's a problem. This is not a 6 to 8% transit depth. And in fact, metals and high metallicity outflows are not sufficient to explain this 6 to 8% depth. You can see here on the left, the cartoon that Papenhager presented for that transit depth, that's that 6 to 8% in blue. And even when we increase the metallicity to, say, 10 times solar, where the expected metallicity of HD 189 has been constrained to be about 3 to 5 times solar, is not sufficient to explain that. So a pure spherical outflow with high metallicity is not going to explain this extreme transit depth, even though we get decreasing mass loss rate, and I'll talk about that in a minute. So what else could it be? We could be seeing even more enhanced metallicity, perhaps something like increased iron, or maybe we're getting a Haber-Situ ratio. It could be something like 3D geometry is going on here. You can see in George King's thesis, and I think their current observations also agree with this, that there may be a leading bubble here, something to do with like stellar wind confinement perhaps, or it could be an effect also of the limb brightening that occurs in the X-ray. And George has a poster in session 2. So how is that going to affect our outflow energetics? I'll move quickly through this. Metal line cooling is going to be significant at high metallicities. We've already seen that. High flux is well known. Ruth mentioned why it's at high surface gravities as well too. We can see here on the right that oxygen line cooling becomes significant. I have a wonderful undergraduate student who's been working on pure steam atmospheres. You can mark that down on your bingo. And he has found that oxygen cooling can become incredibly significant for these pure H2O atmospheres, even at very low metallicities. Or that was the last planet. This is high metallicities, obviously. We do see a decreasing mass loss rate when you have these high mean molecular weights. And in fact, it is the high mean molecular weight and not the metal line cooling that is causing this depressed mass loss rate. Because when we turn off that line cooling, we still have a slightly more elevated mass loss rate. Mass loss rates, our final point here, we are going to see this incredible trend, which I'm very excited about the implications of this for things like the cosmic shoreline. There is a much sharper decrease in mass loss rate as a function of increasing metallicity for lower surface gravity planets. And as a function of increasing surface gravity, you get a much shallower relationship with metallicity. And just to apply this to some planets, Shreyas Esivagada, who is also here, looked at some planets at the top of the Neptune desert. These are mostly hot Jupiters, and I'll show those relationships really quickly. We are able to get good agreement with the observed values in black, and I agree it's a terrible color scheme, but bear with me. By increasing the metallicity for these planets, we are able to find that most of them are about in good agreement with, like, somewhere between 1 and 10 times solar, including WASP 80b. By increasing the metallicity, we're able to match that observation for the mass loss rate. Not quite so for NGTS 5b, but getting closer with increasing metallicity. WASP 177 also well agreed. Unfortunately, WASP 52b not in great agreement with increasing metallicity, which then agrees with the conclusion that Shreyas had about this is perhaps something else like stellar wind or magnetic field confinement, or something about stellar contamination. And Shreyas and Andrea Calroy, whose results are plotted here, are also at this, and please go see their talks. Talk to me about these things, please, if you have an open source atmospheric escape model that's not listed here, or you don't like the bio that's listed next to your escape model. I'm very interested now in cosmic shoreline stuff and rocky exoplanet escape. And if you have some complaints or want to use Windy, please talk to me about that as well. And I'll leave up my conclusions.
Awesome, thank you. Questions? was curious whether with the X-ray transits, are there any other planets that are remotely good targets or could be observed to get additional information?
I think my assumption, and observers in the room can correct this, is that a lot of these planets that will have metals in the outflow should have a larger cross-section to X-rays than, a planet would look in the optical. And so I don't know why, in fact, we have not observed this in other planets. Perhaps it is the particular mass loss rate of HT 189 that makes it a good candidate for this. But hopefully someone else can find some more.
Question in the back.
Do you think in the future it would be possible to couple this with a code that it can extend out to get the tail?
So Jess asked if it would be possible in the future to couple this with a code that extends out to get the rest of the tail. I think that does require more 3D physics. I think we can make some simplifying assumptions about how the density changes as a function of distance from the planet and as a function of, the cross-section across that outflowing tail, that torus of material. And I know that Ethan Schreier has worked on making some models for what the density structure of that tail and torus look like, so that we could possibly do it analytically, but it will vary so much depending planet to planet on things like stellar confinement.
Awesome. Time for one quick one.
Curious Tafuri, Vanderbilt University. I'm wondering, when you tested different SEDs, or if you tested modifying the same SED a little bit, what particular regions of the spectrum make the most difference? And also, the smoothing choice, does that make much of a difference to the results?
So we had an excellent question about which region of a different SED is going to make the most difference on our outflow structure and whether or not the smoothing choices affect that. Smoothing choices, no, we've tested this with the full high resolution spectrum, and it does return the same results as the smoothing algorithm. With regard to what part of the spectrum makes the biggest difference, it is going to depend on what species you have in your outflow. So you saw in the example of pure hydrogen helium that we saw that inversion of which hydrogen and helium are ionized first. That's because the ionization energy of helium is 24 eV versus hydrogen 13.6. And so say there was more energy in past 24 eV, you would get more helium ionization, but if all the energy was sequestered maybe between 13.6 and 24 eV, you would mostly get hydrogen ionization as a result of that. So it really depends on what the species are and what their ionization energies are.
Very cool. I think we're out of time. So let's thank Madelyn again. All right, so next we have Anna Taylor, who's going to tell us about exploring atmospheric escape from hot Jupiters and water-rich sub-Neptunes with full atmosphere models. Take it away.
Thank you. Can everybody hear me? Okay, good. Hi, everyone. My name is Anna Ruth Taylor. I am a third-year PhD student at the University of Arizona, and today I'll be telling you about some work I've been doing on the helium line for hot Jupiters and sub-Neptunes. So I'm going to kind of cut to the chase here. We all are here because we care about atmospheric escape. I don't really have to motivate that. But the helium, the metastable helium line, or maybe referred to as the helium triplet, is the line at 10,830 angstroms. And in this kind of canonical exoplanet population plot, I've highlighted all the non-detections in blue and the detections in pink. And you can see that our detections are kind of all over the place in this parameter space. And this begs the question, why is it detected on some planets and not others? If we fold this even deeper and we try to look at proposed scaling relations that have tried to relate what is basically the strength of the helium line to essentially the energy limited mass loss rate, you can see that there's a lot of scatter and a lot of outliers in this plot. And I'm particularly interested in why there are so many outliers and when there's an outlier, why. So to this end, me and my collaborators have developed a full atmosphere model to interpret the helium and hydrogen Balmer lines. This model includes a coupled framework for the full atmosphere, so lower, middle, and upper layers. It includes updated and extended rate coefficients for metastable helium, and all of those are in the paper that I published over the summer. And it includes multi-species transport and energy balance, which means that we can explore processes like molecular and eddy diffusion, and we do energy balance, so we're not assuming anything about the temperature in the atmosphere, we're solving for it. So we can use this model to ask what controls the shape and the strength of this helium line. Are the recent proposed scaling relations valid in all circumstances, and more importantly, if not, why? And how does the atmosphere structure and helium line change for different types of planets? So I'm going to go kind of through the model framework. We start with an established lower and middle atmosphere model. This is a photochemical model that does this equilibrium chemistry and solves for the temperature structure self-consistently. We use this for the lower boundary conditions for our multi-species 1D upper atmosphere escape model. And normally I would never do full model equations on a PowerPoint, but I thought it might be interesting to you guys. So we'll go through them, I'll explain all the terms, and it'll be not scary. So this model is governed by 3 equations, and Ruth did a great job introducing these. First, we have the continuity equation, which says that the change in species mass density over time, plus the radial flux of species, including species-specific velocities, which I'll get more into how we calculate those, is equal to the sources and sinks from chemistry. So this is basically like you can't create or destroy matter. Pretty good. So next we have the momentum equation, which states that the change in momentum over time plus the momentum transport from bulk flow and pressure gradient force is equal to gravity plus viscous forces. And finally we have the energy equation, which says that the energy change over time plus energy transported radially by the flow, so advection, is equal to radiative heating and cooling, plus the adiabatic expansion cooling, so this is PDV work, plus thermal conduction, so this is heat going from hotter to cooler regions, plus viscous heating, which is kind of like friction. So back to how do we calculate different species velocities? We do this using the diffusion approximation. So this states that diffusion from concentration gradients, so this includes molecular and eddy diffusion, plus diffusion from pressure gradients, minus the ambipolar electric field force. This is a force that occurs when in an outflow that is ionized, the electrons will escape more efficiently because they are very light. And so you'll have heavier ions down below, lighter electrons up above. And so this creates a magnetic field that can drag the ions out. And all of this is equal to the collisional drag between species. So fast species can drag the slow species out with them. And I'll note that this is faster than doing individual momentum equations for each species and has produced similar results. Okay, not so scary. So back to the model framework. So we have developed a helium level and a hydrogen level population for the upper atmosphere. And then once we have the lower and middle atmosphere in the upper atmosphere model, we plug this into a line of sight transit depth calculation so that we can compare to the observations. So for this study that I submitted yesterday, yay, we first started with everybody's fave, HD 209-45-8b. This is kind of the base of our study. It's an archetype hot Jupiter. It's very well studied. We moved on to the elusive HD 189-733b, similar planet, but for the helium absorption in most observations is much broader than expected compared to HD 209, like twice as broad, and we're not exactly sure why. I'll also note that for both of these planets, some models have had to use subsolar helium-hydrogen ratios to match the helium line, meaning that if we used a solar helium to hydrogen ratio, we'd be overestimating the line. Next, we model a very similar hot Jupiter, HD 149-026b. So this is a similar hot Jupiter, but there's no helium detection. So essentially, based on these scaling relations, these 3 similar systems should have similar strong helium transit depths, but they all have different transit depths in their own right, and I'm interested in why that is. And then finally, we extend our model to a sub-Neptunes. Yay, cool kids are doing sub-Neptunes. So we start with the archetype JG 1214b. So with this model, we can kind of investigate the impact of different compositions on the helium depth. And this one is extra spicy because it has a debated helium detection. Okay, so if we plot these 4 worlds on this proposed scaling relation, we can see that JG1214b and HD209 are lying pretty well on the line, although it does depend on which observations you use. But you can see that 149 and 189 are far off the line, and let's try to figure out why. So I'm going to flash up a slide like this for all of the planets. So I have the temperature versus velocity, or sorry, temperature versus radius, and the velocity versus radius here. And then on the left, you can see the modeled helium, and on the bottom, the hydrogen transit depths. And so we get a mass loss rate similar to what has been derived in the past, and with a photoelectron heating efficiency of 40%, which is a free parameter in our model that describes how efficiently photoionization heats up the upper atmosphere, we match with the metastable helium line and the H-alpha line wall. On to HG189733b, you can see that this has a very similar temperature structure, similar velocity structure. It's a little hotter, it's around a K-star, it's a little closer. But with a similar photoelectron heating efficiency of 30%, we match the depth of the helium line well. But in order to match the width, we had to introduce 12 kilometers per second, that's a lot of kilometers per second, extra broadening into the model to match the width. And for the H-alpha line, you can kind of tell both of these models with the not extra broadening and extra broadening kind of match. Finally, for HG149026b, again, similar temperature structure, velocity structure, heating efficiency. Our model is consistent with a non-detection for helium and H-alpha. All right, so to summarize these 3 hot Jupiters, again, scaling relations would predict that these helium lines should be similar, but the observations are inconsistent with this. So to explain the width of HG189, HG189 is a problem child, I guess. It must have some broadening mechanism that is hard to explain with our 1D model, so your brain automatically goes to like winds, 3D effects, magnetic fields, something like this. And the reason that HG149 has basically no transit depth is because it has higher gravity, which means we already saw earlier that this means it will have weaker escape, and this causes strong diffusive separation between hydrogen and helium. This means that heavier helium is being left behind by lighter hydrogen in the outflow. We actually see diffusive separation between helium and hydrogen in all of the models. You can see that the white line is the solar helium to hydrogen ratio. And if we go through all the models, we can see that the helium is dropping off. It's just especially apparent for 149 because of the high gravity. So this diffusive separation could potentially be the physics to explain why other models have had to use a subsolar helium to hydrogen ratio to match the data, and why we have overestimated these lines. All right, so let's move on to the sub-Neptune. So we have the temperature and velocity structure, and you can see that we're in a completely different regime of escape here. We're at much lower temperatures, more efficient escape. And we first did an atom-only model, mostly for comparison, but you can see for this sub-Neptune with an atom-only model, we are way, way, way overestimating our helium transit depth. So let's try to make this model more realistic. We can see from our lower and middle atmosphere model that at the lower boundary of our upper atmosphere model, which is at a microbar, that helium and hydrogen aren't even close to being the things that are dominating in the atmosphere. You have H2, CO2, water, CO dominating, and then helium, and then atomic hydrogen's not even on this plot. Specifically for JG1214b, also, the JWST data is matched much better by really, really high metallicity atmospheres. So this motivates us to include H2 in our model as a first step. So new things in this model are H2, H2+, H3+, HEH+, and the chemical reactions related to these species, and of course H3+ radiative. So with this model, we can see that the temperature structure and velocity roughly similar. The escape is less efficient, and so it's a little bit hotter. The mass loss rate has gone down. And in this yellow transit depth, we are matching the observations much, much better. Now for a toy model as a first step into including other molecules, I included CO, CO2, water, and into into the model as tracers, meaning that they are interacting with the momentum equation, but I don't have any chemistry yet. So you can see that this makes the mass loss rate, higher mean molecular weight, lower mass loss rate. And as expected, that tracer model gives a slightly lower helium transit depth. So with this model, we can explain why these dots are so far off the line. For HD149, there's no transit because high gravity leads to diffusive separation between helium and hydrogen. And for HD189, again, my 1D model can't explain 3D processes, but it almost seems like it gets broader instead of deeper. Who knows? All right, so my key takeaways are that the observed helium transit depths do not always follow simple scaling laws, and the line strengths are shaped by diverse processes. High gravity, and specifically high gravity plants are showing strong diffusive separation, even between hydrogen and helium. Our full atmosphere framework reproduces these observed trends across 3 hot Jupiters with similar photoelectron heating efficiency. And finally, like we heard before, sub-Neptunes require different physics. We can't assume helium, hydrogen anymore. We have to do molecular chemistry, dang it. And obviously, we've seen that radiative cooling alters atmospheric structure. And my plan next is trying to add water chemistry into this model in full. So you can scan the QR code to read the paper I published and contact me. Thank you.
Awesome, very cool. We got time for 1 or 2 questions. Yeah, Will.
Yeah, Will Meisner from Carnegie Lab. Really interesting talk. I was wondering, for the helium-hydrogen diffusive separation, is that assuming like a diffusion ACC or something like that, or is that something you're calculating?
Yeah, so the degree of diffusive separation will depend on the KZZ, and the KZZ that we use is derived from the lower and middle atmosphere model. RFOX 2023, if you're more interested in how we did that.
In the back there.
Hi, Ethan Schreier, UCSC. Where in your models is the helium line formed compared to the H alpha line in the planetary atmosphere? And what does that tell you about what could be causing the broadening?
This is a great question. It's I'll answer your first question, but it's actually from something else. So the helium and H alpha line, it kind of depends on where the atmosphere becomes fully ionized, since the H alpha line is mostly formed from neutral hydrogen, and then the metastable helium line is mostly formed from He+. And something I've explored in the paper that I just submitted is, we see this really broad line for something formed with ions, but then not as broad line as something formed with neutrals. Wink, wink, maybe it's magnetic fields.
We got time for one more. It's Colin.
Great talk. HD189733B, is that what it is?
Mm-hmm.
Is known to have has shown a lot of variability in the Lyman alpha transit, and there's been other cases of potential variable escape. Your first bullet point seems to say that lots of things can affect the line depth. Can you say anything about variability within a system, like for one planet?
Yeah, so totally. So for the paper I published on not HD189 but HD209, we explored, the effect of stellar activity, varying KZZ, the effect of adding metals into the model, and all of those things affect the helium line a lot, and the H alpha line less so, which is kind of promising, because if we could get both of those lines together, that could kind of, erase some degeneracy there. But the H alpha line is less affected it's less sensitive than the helium line.
All right, let's thank Anna and all of our session. All right, and then you guys can go take a coffee break. We'll come back at about 11 for part 2. Speaking in wants to come up.